All right. Good. We got a recording working. All right. Cool. Oh, we lost Jessica though in the process, but we gained a Christine. That's good. All right. Yeah. So I guess today, always open for discussion. Do you guys have any questions? Anyone have any questions? Who's here?
I have a question.
Yeah.
So one of the tests on the data that I was going to do didn't end up being, isn't a machine learning based test. It's just like a metric, like it's one way or the other. Like what would be a good way to present that? Would you do a train test split? Because
yeah, that's a good.
Run the test on someone. Yeah.
That's a good question here. I'm just going to share my screen real quick, so in case I want to write something down, make that. So, Mike, could you maybe give a little more detail? So you're saying that, like, you said it's a metric, or
it's an NLP situation, and so it was like the percentage of capital letters in the title, and so if it was below a certain percentage, it was going to be fake news, and above, true. So, like, how would you, I guess, run it on a subset of your data and be like, this is what you get, or all the data?
Yeah. So this is more in the sense of like what you tell your audience and like trying to show
I guess even in a Jupyter notebook or.
Yeah. So a good rule, like this is kind of like the scientific part that you want to focus on, is you do want to do a train test split, right? Yeah. Because if in the end your ultimate goal is to detect, let's say, fake news in this case, right? Yeah. You want to be able to say, oh, we figured out, like, let's just pretend like, oh, we figured out, fake news has 50%, capital letters, and then you want to use that metric then for data that you haven't seen yet, right? You'd want to make sure that you actually split it and say, okay, this is data we haven't looked at yet, it's randomly chosen, right? And then we see, okay, does that metric still hold for this data set, right? And then that would be kind of like, say, okay, like, how well did it perform? Saying like, okay, did it do a good job or not? You can, like that, you'd still want to do it in like a Jupyter notebook in some case, right? Presenting it to your audience is, you might actually go, okay, like, we have this idea that maybe we just need to look at how many percentage of capital letters there are, just to kind of see, like, maybe this is like a baseline, just kind of an idea, like really simple metric, see how well we do. And so one thing we wanted to do, like you kind of introduced this, like when we tested this out, we wanted to make sure we took some information, like some like the article, some data points that we haven't seen yet. We're going to keep that to the side. We looked at the rest of the data and said, oh, we found that 50% of the letters are capital in fake news. So based on, this data that we took a look at, right? Okay, we're going to base it on that. And then we tested it out on this data that we haven't seen yet. And we saw that it matched up. We saw it didn't match up. We saw it didn't do a good job. Said it did a good job, whatever you want. And that would be kind of like how I'd maybe present it and explain it to the audience, and being like, introducing the idea of like, we're keeping some data that we're not looking at yet to see how well we will perform. And you can even say, oh, we randomly selected it. Do you have to use a test train split terminology? I would say probably not. I think that might actually be more confusing for a lot of people to say, this was our training data. You can kind of subtly point towards it. It's like, oh, we trained, like, I don't even know if that's the right way you want to present that, but like, oh, we like looked at the data from the set, you can even say, oh, we call it our training set, but I probably would even avoid that. Say we took this set, we learned from this data that 50% is capital letters, and then we applied that to you can call that probably our testing set, because that's probably a little bit easier. It's like, oh, here's our test to kind of see how well we performed. And then what's nice, if you do have something like that, where you're like, oh, here's a baseline model, and like you plan to do more, you can say, reference back to, oh, we use the same like randomly selected things as our tests. And you can kind of say, oh, this is how well it performed. That'd be kind of maybe a way to present that.
All right, thanks.
Yeah, no problem. It's a good question, because it is tough sometimes doing this machine learning modeling and then saying, how do you present this to a non-technical audience? Like, how do you talk to someone about machine learning without them ever knowing what machine learning is and the concepts you're supposed to use? So yeah, good question.
The more I learn about, evaluation metrics and stuff, the less I understand what the use of accuracy is. Because it
Yeah.
seems like it seems like accuracy is not a good measure for too many things.
Yeah, accuracy generally really isn't. Um, it's I think the only time accuracy really makes sense is when you're comparing two things and you really care about saying how well did we accurately measure, you know, like for example, a positive and negative like tests is like like what was our accuracy when we had a negative test? You know, were we able to accurately predict it was a negative? Um, that's really the only time it really makes a lot of sense. Um, it's a general term in like people's vernacular that's kind of matches up with what you are saying, right? Versus like if I say recall, people don't really, unless you know what recall is, people don't really know what that means. Even like standard deviation, I think people kind of get an idea of it, but maybe not. Accuracy, people are like, oh, I know what accuracy is, which is also why you have to be really careful about using the term accuracy, because we know what accuracy entails and like what the issues are, whether we have high accuracy or low accuracy, and it's actually not reflective of what we want to represent. But people will think that they know what accuracy is. So I personally try not to report accuracy unless I want to specifically emphasize, like, you know, like for example, the testing negative. Like, oh, like we predicted it to be negative and we were accurate 98% of the time when it was negative.
Yeah, I think I find that most of the times it's going to be like recall or precision, depending on which way you're
Mm-hmm.
going, right?
That's right. Yeah.
Do you
And
want to do you want to measure whether your data
mm-hmm.
has too many false negatives or too many false positives? Which one affects you know your,
Exactly. And
your
that's
use
mhm.
case more?
And that's exactly like as a data scientist, you generally will focus on that more. Like, and that's when you have like F1 scores or F beta scores and saying like, okay, like F1 scores are going to be basically balanced, right, between precision and recall. And usually those are the things that guide us more than accuracy by itself. But then you also like very rarely actually say recall, precision, F1 score to a non-technical audience, right? Because they're not going to know what that is. And if you do bring it up, you could try to explain to them, but then you're just going to turn your presentation to explaining how to do F1 scores and stuff like that. That's why I always tell people, like, especially for classification, it's really useful to like use the confusion matrix to get an idea of like what things are doing positives and like what things are being misclassified, what things are being classified correctly. And then I tell people, don't show a confusion matrix to your technical, like non-technical audience. I actually think it's a little too technical. This is my opinion, but
You
I
mean
think it's a little,
we're gonna confuse them?
yeah, exactly, right? Like it's meant to be confused, and you could say this is a confusion matrix, and people are like, yes, that's correct. It is a confusion matrix, but instead of trying to explain to them like what a confusion matrix is, it's usually easier to say, well, what do you want to talk about the confusion matrix? And usually, like if a confusion matrix, you're looking at something, you're like, oh, like these areas are where it's, you know, the model's confused, right? And so you identify, oh, it misidentifies this case for this thing. Oh, I should probably, you know, like that happens because of this reason, or oh, that's really important because this class, like the traffic sign example I had before, this class is the stop sign, and like it's having a hard time between stop signs and like, I don't know, proceed forward signs. I don't even know if those signs exist, but like you want to make like, oh, these are where it's messing up, and like, does that mess up make sense? Does that show something about the model, like performance? Like, what is the model seeing in there to make that mistake? And then saying, is it relevant in the sense that like, this is an acceptable amount of error for that class? And that's the stuff, all those terms, like all those questions I just said, could be answered and explained to the audience without having to use any technical language. So that's kind of like where I say like, oh, you'd probably have something like bullet points or some kind of emphasis there versus just, I see a lot of people, not that if you guys have done this, don't worry about it, but like people will put a confusion matrix and like just say about like how that confusion matrix relates. And I think like in the end, people's eyes glaze over that and like they might see what you're saying a little bit, but they're not going to remember that coming out of their, you know, presentation. Yeah. But yeah, anyway. Yeah. Yeah, accuracy, like you said, Alvaro, accuracy definitely is like one of those things where I'm like, it's fine sometimes, but whenever someone starts quoting me accuracy, I just kind of like internally kind of like squint my eyes a little bit and say like, okay, but what else? Like, tell me something more than the accuracy. And like, see, people report F1 scores, which I'll be honest, like unless you're kind of more familiar with F1 scores, you might not have a super strong like intuition of like what a good F1 score is and what that means. And so just kind of, I think that takes practice and stuff. So my big thing is like in the end, all those things are saying accuracy, precision, recall, F1 scores, F beta scores, it's all summarized essentially in the confusion matrix. That's all that's based around. Like if you have a confusion matrix, you know all that, and you can derive all that information from that. So that's usually a good place to start off as you're trying to evaluate. Let's see, one other thing, modeling. When you guys do models, a lot of times, like for example, like neural networks, especially where you have different epochs, people will kind of report accuracy like over time. I don't think that's a good view of like what the model is actually doing, just because again, the whole point of accuracy, it can kind of fluctuate in there. A better accuracy thing is usually some kind of like whatever your loss metric is. So if you're doing regression, it could be MSE. If you're doing something like classification, you'd have those kind of metrics in there, categorical cross entropy, for example, or if it's binary, right? And the reason why I say plot those, like you guys know what I'm talking about, like say plot the validation versus like training, right? You guys know what that means. Yeah. The reason why I say plot those is because that's what the model's learning off of. Like that's what we're saying, oh, how the model knows to do better or not is based off the loss. So you might as well use that because then you can see how does the model actually do. And this is where like, if you have those different, let's see here. If you have like your, like this is your graph right here. This is like the loss. Oops, that's not loss. This is loss. And this is like, this is actually like on the bottom here, I'm gonna call it complexity because it doesn't have to be like a neural network, but usually when you see this for neural networks, this would be like epoch, right? How many epochs it goes. But if you get something that's not this, you could have something like, number of splits, for a random forest and stuff like this. Could be like the more splits you have, the more complexity you have in that model, right? So in general, what you'll see is that your loss, if it's very, very not complex, basically the very first epoch, it'll tend to be for the training will be very high, and then it'll kind of drop down a little bit. And what you'll see almost every time is something like this. Real quick, if you see this, like this is pretty smooth, but sometimes you'll see things like bumpy like this, like going through. What could cause that bumpiness, like from your model training? You haven't got an idea? Yeah, so one way this can happen is if you have regularization going on here. So the thing is like, the model's improving, for example, and getting more fine-tuned, those points, which technically will lower the loss. But if you have regularization built in, whether it's L1, L2, even dropouts for like neural networks or a type of regularization, it's going to technically, it's like, oh, it should do better the next round. Well, if you start punishing, because of regularization, punishing more precise values, more values like this, the loss is actually going to jump up a little bit, right? So you might see a little bit more of a, even in the training, a little more bumpiness and stuff, but that's expected. So in general, if you don't have any regularization, it's pretty smooth. So that's your training right here, right? But then if you have your validation is going to do all the really interesting stuff. And that validation, I'm going to use this here. I'm going to use blue. I didn't do a good job of doing different colors if anyone's colorblind, but validation will typically be underneath, like, not underneath, it'll be a little bit above the loss over here. It's going to have a worse loss, right? So it'll tend to be up here. And a good model, like an ideal model, and let's say this is the end where you stop it, would be like right about here, right? Like that would be, this is actually a really good model. Like, hey, that's pretty good. And then if we were to continue on, like if we do more complexity, you probably would see this like come up, right? You're like, good, you got the lowest point right before it came up, right before that inflection point, right? Well, I guess it's not really inflection, but like when it starts changing that direction, right? That's the ideal model. Now, of course, as you guys probably have seen already, that's not always the case, right? So one thing you might see is one typical one that a lot of people see, will see something like this. Like it's kind of bouncing all over the place. And so does anyone know what's going on here? Like why is it all bouncing, not smooth? Besides the fact that it's like not even close to like a good value.
High learning rate.
Yeah, so high learning rate, so like high alpha, right? If you're talking about like neural networks and stuff like this. What does that mean when we have a high learning rate? Like, why does it bounce around when we have a
Uh,
learning rate that's too high?
because it could go past the minimum, bounce over to the other side, and then has to come back, bounce
Mhm.
back to the side it started from, and it could just go like boom, 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 boom.
Mhm. Yeah, that's right. And when you talk about minimum, you're talking about the minimum of the cost function J, right? It's like
Hmm.
saying, oh, this is the minimum down here. This is where we want to end. But the model says like, okay, it's at this cost part, but it does a big step because it's a big alpha, and it steps over here, misses the minimum, takes another big step, but let's say that big step is really high, goes over here, and then goes over here and bounces around like you were saying, Alvaro. And basically, it's never getting to that minimum. It's sometimes getting worse, which is what you see here. So if you see this, right, one solution is like reduce like your alpha, your learning rate, right? Other ways you can do this is regularization, right? This will kind of help smooth things over where it's not trying to bounce out. Optimizers can also do very similar to like lowering the learning rate or a learning rate scheduler. That way it doesn't keep bouncing around. So typically this will happen when you basically, you're bouncing around that minimum, right? And it's having a hard time finding that part. So reducing alpha, turning on regularization, using an optimizer can usually help this problem. Another way this can happen too is if your validation data set, assuming this is green is in training, the blue is validation, your validation might not be have a lot of variety in it. So even though the training loss is doing better, it's having a hard time fluctuating. So this happens if you guys had done Mod 4 project and you use the validation of like the 16 images in the validation set. I don't know if you guys have all seen that, but in the data set for Mod 4 for the image recognition for chest x-rays, you actually see there's very few images in there. Like I think it's only 16 in the validation. You might see this bouncing around because there's just not as much variation in the validation set. And so you might see it bounce around and then you might get them to zero.
I went and worked with the Mandalay set, which is a
Mhm. Mhm.
much bigger data set. So
And that's the way you can do it too. Like if you use the Kaggle data set, it's already broken into 16 images, which is what you might see here too. And which is kind of a sense of like you are having a hard time converging because there's only like 16 images to test against. So if there's one weird image, your minimum basically looks like this, and then kind of goes up like this. So you're kind of bouncing around a lot outside because you're kind of missing this spot. But also in a lot of ways, should you even care about this minimum? Because there's only 16 images. So you should really get something that's going to be having a much better cost function. Okay, makes sense? Cool. All right, so I just want to show a little bit of that. So ideally, I'm showing you like all the things that can go wrong, right? The other thing validation can do is the validation training. You might see something that's more complex that goes up and then kind of like it staggers like this, right? And that means it's like, oh, we're underfitting at this point, right? Because this basically stopped learning right here. So that means that usually your model needs more complexity. I call it more complexity. It means like you can, for example, in a neural network, increase the number of layers. You can increase, what's it called? Different hyperparameters and stuff like that that add that complexity in there. Another way we can add more complexity is have more variety in your data, right? So like you can do data augmentation, you can collect more data, right? So the idea there is like we can have the model learn more about this. It's underfitting. Opposite of underfitting is overfitting, and overfitting basically looks like it'll usually start off like this and then kind of take off like worse. So this is the worst case scenario. And the idea here is that it's overfitting because basically, even though the training loss is getting better and better, right, this validation loss is getting worse and worse. Basically, it's getting really good at this training set, but is actually having a bad time generalizing. And that's where you're like, oh, that's not good. And usually we can stop this pretty easily by using early stopping. I could go back to this point right here. This is the best point. But in this case, if you're like, oh, this is really bad, even this point, like right here, is not good enough, you probably want to reduce the complexity in some way, right? Is basically your model's being too certain, it's being too precise. So sometimes regularization can kind of help out with this. So think like neural networks drop out, L1, L2 can kind of help doing that because it's being too certain. Other things you can do is like just reduce like what you think of complexity. So sometimes people like neural networks will have too many layers or too many neurons, and then you'll tend to have this extra complexity. Other thing too, this can be like, this is wasted time, right? Like if your models keep doing this, like you probably should have stopped it like way before, because basically it's like, oh, it's getting worse and worse. It's not going to get any better. Okay, cool. Yeah, that's kind of like the three main things you'll see. It's kind of like this kind of curve, something that's underfitting, and then we have something like I showed, like kind of bouncing around, which means that this model is having a hard time. We call it converging. It's not converging to a specific answer and stuff like this, and that's a different kind of problem as well. So those are kind of like the three most common things you'll see in your neural network training, or not neural network, but like model training in general. Okay. Any questions on that? Pretty good. Cool. It's useful to kind of bring that up. I think technically tomorrow I'm supposed to talk about model iteration. That's kind of related to it, but we talked about it now, so why not? Cool. Any other questions that you guys want to go over? No? Pretty good. Cool. All right. So.
Wait, I do have a question.
Oh yeah, go ahead, Jessica.
And I feel like thanks. I feel like we maybe had gone over this in the past, but when it's failing to converge, like I know when I was training my time series model, or wait, what was I doing? Yeah, I was training my time series model. Oh yeah, I was finding which model, which set of orders gave like the lowest BIC, so minimizing cost. And some of the models that weren't that good, I would get the warning that they failed to converge. Can you just talk a little more about that?
Yeah, so is this more, you're saying you get a specific error that says failing to converge, or just more like you're observing?
But they were the models that wouldn't have been good anyway. But yeah, so sometimes it would pop out the warning that it failed to converge.
Yeah, and could you repeat then what kind of models were these? Like, was this time
series? So a Ceramax time series model, and I was searching for the optimal set of orders. So
okay, I know to be honest, time series is not my specialty, right? So I'm gonna kind of go off of like what I think is going on there. To be frank, that someone might know more about time series than me for sure. But from my understanding, when it's like failing to converge, what's happening is, how do I explain this? So I don't know if we talked about this. Time series is really just like linear regression, but of the time steps themselves. I don't know if that makes sense to people. So maybe it kind of helps a little. I see a couple nods, but I think it might help a little bit for me just kind of draw this out. Is that when we do linear regression, right? If you guys remember way back to mod 1, right? I think it was mod 1. We had like y hat, right, which is our prediction, is equal to some value a1 x1 plus a2 x2, right? And then I'm just going to stop there. You could have multiple ones, right? And then like plus usually like a final constant, which I'll just call like a naught. Okay, so like something like that. Technically, you could do like x naught, and then it's just x naught is 1. So this is like, or to the power of 0, which is like just 1. So you just say like there's some constant or intercept and stuff like this. So this is like linear regression, right? So if you guys remember, I don't know if you guys ever came across this, but when you did linear regression, maybe for the first project, if you try solve, because like all this is basically is an equation, right? Or not an equation, a matrix, right? And we're trying to solve for that matrix. And one of the ways we can solve for that matrix is something like matrix decomposition. So SVD is one way, and basically one way we can do that is essentially trying to invert the matrix and then use the inverted matrix to basically like like you think back in algebra, if you guys like y equals like m times x or whatever. To solve for x, we divide by m, right? Well, if m is a matrix, you can't just simply divide by m because there's no divide in like matrix algebra. You'd have to do like m or y equals the inverse of m, which is m's the matrix here, times x, and you have to do it inverse over here on the left side because matrices matter if you go left or right multiplication. And that could solves for x, right? Completely. The problem is actually finding this inverted matrix. That might basically be really hard to do. And one of the strategies we do is basically we can do like SVD. We can do different strategies to find this matrix here. So what happens though is that if this is really difficult to find, or if the values are really, really big, this can be hard to find. Like it ends up being, I think it ends up being to solve a matrix completely. if you have like n elements in here, I think it goes n to the power of 3, or n to the power of like, I think we can do like n to the power of 2 point something. But like basically, if you have 100 times bigger, it's going to be even harder to find that inverted matrix. And so if you remember that, then it's like, oh, that means that sometimes linear regression, if these values are too large and we don't scale them through, or they're too small and it's very difficult to find this like matrix stuff, we can have issues just for trying to find this matrix. This isn't the only way for us to find the solution, like the best, there is an actual best equation. We can say there's a mathematical way we can find the best equation. Finding it though can be really difficult. So there's other things we can do like gradient descent and stuff like this to kind of like help us like get there without having to do the actual figure out what this inverted matrix is. But if you think of it in this terms, then time series, it being a linear, like another linear regression, but instead of having like x1 being like a feature, x2 being a feature, x1 is like that point in time, x2 is the next point in time, x3 is the next point in time after that. That's kind of like what you're what that looks like for a time series linear regression. If you think of it in that terms, you can get the same issue where basically you fail to converge, where it fails to find this inverted matrix because the values are too large or too spread out and stuff like this. That's kind of my understanding when you get that error from trying to solve for serial max, because in the end, it's really just trying to do a linear regression. And so you can have that same issue. Okay, I don't know if that made sense to people or that helped Jessica.
Yeah, that makes sense.
Okay.
Thanks.
No problem. Yeah. So one thing you can do maybe for that situation, like you were saying, like converging, is you might need to scale features that could help, or using a different strategy. And it just depends how the library works. Sometimes you can use a different strategy to do that. And again, this is where I could say like, I am not a time series expert, so like I'm not sure exactly what would be the most ideal strategy, or even all the different strategies you could use. But that'd be kind of my next guess, is that how you could avoid that issue. So yeah, good question though. Yeah, I wish I could tell you more about time series in general.
No, that's super helpful. And then I did find too, like if I increase the max iterations, it would take longer and like fewer of them would fail to converge. But it was like usually the models that wouldn't have been good anyway. Do you know what I mean?
Okay, I think that makes sense. I think maybe it has, maybe the fail to converge error then is talking about like it's trying to find this like inverted matrix, for example, but it's taking a long time for that to actually get to. So if having more, essentially more steps, right, might allow it to have a bigger buffer for it to finally find that convergence. Because again, like the more terms you have, like, and it gets up significantly. So that's probably what it's hitting. Yeah.
That makes total sense. Thank
cool.
you.
Well, I'm glad it did. I think it made sense to me too. So cool.
Perfect.
Awesome. All right. Any other questions you guys have? It's all been really great questions, by the way, in situations. Yeah, pretty good.